Hello, I'm Justin Ridgewell. This is the last talk of the day, the magic behind how AMP validates and transforms its code. To begin with, we need to start with a simple premise. Large code bases are difficult. As the code base grows larger, as more code comes in, as more developers start contributing to a project, more issues creep in. And these can be bugs that aren't caught during review. They could be slow code that can be refactored and made faster. It could be brittle APIs that you have to call in the correct order or with just the special argument that most people won't know. Or it could just be a dangerous API, like inner HTML letting in an XSS vulnerability into the code. All of these things need to be found. But code reviewers can't be the only ones responsible for this. There's just too much for any one person to know about. And even if they could know it all, they're going to fail sometimes. They're not going to spot every single bug that happens. We can't just rely only on the code reviewers to catch all of these things. So we have to have some kind of automatic validation. Something has got to do this for us so that we can find out what's going wrong in the code base. Particularly, we can take our best practices and put them into transformations, into linters that will allow us to do this automatically. The build system can be responsible for finding all of these bad cases. And the code reviewer can just be responsible for reviewing the overall code, the pattern that's happening, the actual implementation of whatever UI they have. We can ban the anti-patterns, the things that are going wrong that we know aren't going to be used correctly, and we can eliminate those entirely. And we can provide helpful messages to everyone when they do something incorrect, so they know the correct way to use it or the correct method to call instead. And all of this can be done automatically as it happens during the pull request review by Travis. AMP has 3 different ways to do this so far. Originally, we had presubmit checks, presubmit regexes. These are our heavy-handed approach. They're looking for explicit text inside of the JavaScript file. And if they find that text, they're going to throw an error. But these aren't very precise. It has no understanding of what the code is. It's just literally looking for text. It doesn't understand if it's a comment. It doesn't understand if it's a variable name. It doesn't understand if it's a method call. It just looks for text. Next, we have ESLint plugins. These are a little bit more flexible. We can design plugins to look for specific code patterns. Or we can design the plugins to warn about incorrectly formatted code. ESLint is how we run Prettier, which is our automatic code formatter, so that all of our code looks consistent. And finally, we have conformance configs. And these are extremely precise. We can tell exactly what is happening in the conformance config, which API is being called on what type of object. And we can ban it or push people to using a different API. If you think about this, in specifics, presubmit regexes, they look a little bit, they're not great. If you see the console dot, this is a string that we're using as an object key. And we're going to turn it into a regex during the presubmit checks. So this particular one is looking for console dot and then some word characters, and then an open parentheses. And it's looking for things like console.log, console.warn, console.error. And it's going to say console use is forbidden. We actually have a log formatter. I had to omit some of the stuff. We actually have a log source file that controls all of our console use. So srclog.js is allowed to call console methods, but no one else. Everyone else has to call the log methods. And if you have ever read our code base, you probably see a lot of the comment OK, capital OK. This is where OK originally came from, is because we had these regexes, and we wanted to say console OK warn, so that we broke this simple regex test, this simple regex check. Because it doesn't match OK. It's only looking for word characters, and the comment isn't a word character. So we can skip next to conformance configs, which are the extremely precise ones. These are backed by Clojure's type system itself. We can tell exactly what value is being used In this case, we're banning direct access to element.style. So if you have a div and you want to set the absolute position on a div, normally you would just do div.style.position equals absolute. But we've identified issues with this. So instead, we force everything to go through a set of helper methods. One is getStyle, another is setStyle. All these are in the style.js module. But think about it. How do I know what the object is? If I just do foo.style, do I know that's an element? Well, Clojure's type system figures that all up for us. Because we've specified exactly what the argument to a function is, we know it's an element, or we know it's a node, or we know it's just a simple object. And it can only warn us for the cases where I'm actually doing element.style and not some random object.style. So these ones are extremely, extremely precise. But they're a little bit rigid, too. It's difficult to have an abstract plugin that would ban a use case or that would forbid a certain code pattern or something. This one really shines just about banning APIs and nothing else. Finally, we have ESLint plugins. And these ones are kind of a sweet spot in between the really simple regex tests and the really specific conformance config checks. We can write abstract plugins in this and check for whatever thing we want to. But it's not quite as precise as Clojure conformance configs because we don't have information about the types. It's really difficult to know what the return value of a particular method is unless you have a full type system to back you, which ESLint just doesn't have. But in this case, we can look for calls to a function called isExperimentOn and assert that the parameters being passed to it, the second parameter being passed to it, is an explicit string. And what do I mean by explicit string? I mean literally a string literal. Here, if you can see, isExperimentOn, I'm passing a window variable, and then I'm passing the string literal foobar. And we can represent this as an abstract syntax tree. These are really cool. In the abstract syntax tree, it's a call expression to an identifier called isExperimentOn. So it's a call to the function isExperimentOn. And I can check out the arguments that I'm passing to it. In this case, I'm passing an identifier window and then a string literal foobar. But these are a little bit different than what you think about them as. ASTs aren't just about what the runtime value of all these things are. It's how is the code structured? How is it actually written? And we can see code sample 1 and 2 here evaluate to the same thing. They do the same thing. But the way that they're structured is very different. In the first case, I have foobar as an actual string literal parameter. In the second case, I have a reference to a foobar string. These are different ASTs. And I'll explain what I mean. So here's isExperimentOn foobar. Can everyone read this? OK, perfect. Here I have isExperimentOn foobar. And if you see down here in the bottom right, it says no lint rule fired. That's good. We don't want lint rules to fire. Now let's change this to const exp equals foobar. So all I'm doing is taking the string literal and moving it into a variable. Now if we see in this bottom right-hand corner, isExperimentOn must be passed a literal string. This is because we need to grep search for these literal strings to see if they're used anymore. This was a bug we caught a while ago. So isExperimentOn when experiment doesn't quite pass the bar. And it's because now the exp variable isn't a string literal anymore. It's an identifier. It's a binding reference to the exp variable. If I change it back real quick, foobar. We can see it goes back to being a literal. It's an actual string that is represented in the source code. Go back. So right now, if I pass it an identifier, a variable into the function, it says isExperimentOn must be passed an explicit string. But it's pointing right here to isExperimentOn. That doesn't really help me much. I want to know what I've done wrong, and this is just telling me I've called isExperimentOn wrong, but not telling me why, or like not pointing to why. So let's change this just a bit. Context.report is how ESLint fires lint errors so that you can actually see them in your console and whenever you're running your checks. And console.report takes a node which has a source code location and the message. But let's change this from passing in the node, which is the call expression, is experiment on, to being the argument that I'm saying is wrong. And now I can see I'm pointing at exactly the thing that is wrong with my use case here. If I go back to being foobar, we can see the lint rule goes away. So it's telling me exactly what must happen in order for the linter to be happy. And we can go back to having a good code base. And ASTs are, going back. ASTs allow these really powerful things to happen. Once you can actually understand what the structure of the code is, we can take it beyond just lint errors. We can start doing transformations to ASTs, where we can transform, we can have an input code, run it through a transformer, and then have an output code. And these output codes could be auto formatters. Prettier, our code formatter, uses an AST internally. We could have ES6 code transformations if you've ever used Babel. Babel does code transformations using an AST. We can make it do anything. Imagine GCC. That's what transformations allow. And once we have transformations, we can set goals for them. We can optimize for file size. We can optimize for runtime performance. We can enable new syntax features that are not available in older browsers by doing transformations for them. And these are really, really fun to write. I really like this part. So back to demo mode. So in this code, I have an array literal. It's inside of a function called isLayoutAllowed. Array literals are kind of special. They do things. Let me re-describe that. That didn't sound right. Array literals have special transformations that can be applied to them. In this case, it's an array literal, and every element inside of the array literal is a literal string value. These can actually be optimized internally inside of a browser engine. They can be allocated a single time, and then they have a copy on write protection on top of them, so that even though this array literal is being constructed inside of a function call, if I call isLayoutAllowed 100 times, only one array literal will actually be constructed. And it'll just be reused every time and only cloned when a write happens. So this is an optimization a browser can do. But if we look at it, down here in the bottom right-hand side, you can see there's this close quote, comma, space, open quote, and then there's that quote, comma, space, quote again, and it keeps happening. That's a lot of files. That's a lot of bytes that are getting sent down. And eventually, after about 6 or 7, you actually have, you can build up enough of these bytes where it makes sense to do a code transformation on it. We can save bytes by structuring this a little bit differently. So I'm going to just uncomment this for a second. We're going to live demo how we can optimize this to be better for build size. If you see in the bottom right, it's throwing an error right now. I'm just doing this for demonstration purposes to tell you that this is actually matching this array literal. This code is actually running against the array literal. So let's start with it. To begin with, we're matching this array literal inside of the source code, and we're building a transformer for it. So whenever we see an array expression, the array literal, we're going to run this function, and then we can transform it with a little bit of magic. So if I were to console.log path.node, and put this down here, console. OK. That is too small. That looks good. Everyone read this? So we can see It's a array expression node object, and it has elements. And these elements are nodes, and those nodes are string literals. And if I click into one of the string literals, I can see that its value is responsive, which matches the first key and the first value inside of my array literal. This is I have a node that has elements, an array of elements, and those elements are nodes, and those nodes are string literals. That's a little bit too much. So to start with, we can do const evaluation equals path.evaluate. Let's see what that value is, evaluation. So it's an object. It says it's confident. That means I was able to correctly determine what this value is if it were to run in a JavaScript runtime. And its value is an array literal, and its has the elements responsive, fixed, fluid as strings. This is just an array that I can use. And it says true. So if I do something here, if not evaluation.confident, I'm just going to return. And you can see this is still throwing an error, so I'm still matching it. What if I were to change this first key, this first element to be foo? Now, the error is not throwing anymore. What I've done is I've made the transformer unconfident about what the value is at runtime. It has no idea because it's not a string literal anymore. It's a reference, and I don't know what that reference evaluates to. Going back. Evaluation. So if not confident, I returned and I stopped doing things. So if I go back to being responsive, the string literal, I go back to being confident about what the value is, and I'm still throwing an error down here because we haven't finished our transformation yet. So const value equals evaluation. So now I have the value. The value is the array, the actual runtime value, the array literal with all of the elements inside of it. So what can we do with this? Well, what I'm going to be trying to do is we're going to take this to be foo_bar_baz.split. I want to change it to a split function because the split function eventually, after about 7 elements, will save bytes. It's smaller to represent a single string and split on spaces than it is to open and close a bunch of string literals. So, yes. Perfect. So const string equals value.join. Remember, value is an array here, so I can call the join method on it. And I can join the values with a space character. So what is string right now? It's the string, responsive, fixed, fluid. It's everything that I would expect it to be. So how do I put this back into my actual source code, the output of this transformation? Well, I can do path.replace with, I think it's replaced with, I'm calling, yeah, perfect. T.string literal string. And now if I were to uncomment this, you can see in the bottom here, we've gone from having this array literal dot includes to having this string dot includes in the bottom right. So we've transformed from an array literal into a single string literal. But that's not quite right anymore. The string isn't the array that we originally had. It doesn't have the value, and its includes function is going to behave differently. I can now find instead of finding a particular element, I can find any match. So maybe I was looking for the string t. Well, the t is going to match inside of string includes, but it's not going to match inside of array.includes. So we've got to turn this back into an array. We can do that easily with the split function. So we went from like basic things to like, this is going to be a little advanced because I just don't have enough time to explain all of the magic behind Babel. It's just going to happen quickly. So template.asExpression.ast, and I'm going to pass it something. Say foo at first, and then now it changed it to, I passed it foo as an identifier, but that's not quite right. What if I were to pass it foo as a string? Well, it puts the string foo.includes in my bottom right-hand corner. But that's not what I had. That's not the array of responsive, fixed, fluid, intrinsic, any of those. What I really need is my value, string. So I'm going to interpolate the string into it. And now I'm back to having responsive, fixed, fluid, intrinsic, all of these values back into it, but it's still a string. It still says string literal dot includes, and that's not right. But with this interpolation, with this template expression AST, I can do split. And now it says string literal dot split dot includes. But split needs a parameter. It needs to have the thing that I'm going to split the string on. So I can just pass that into the template expression. And if we go back here, we actually see that it's string literal dot split, and then I'm passing in the string, the space character as a string. It's going to split on that value. And now I'm going to do array dot includes, because split returns an array. I'm going to do array dot includes layout. So we've gone back to exactly what we had originally, except we've saved a couple bytes because we don't have to open and close our array literal a bunch of times. And we can actually do some really cool things with this. So what if instead of, right now it's going to cause the split to happen every time. Unfortunately, browsers can't optimize that. It's going to always do a split, which is runtime expensive. It's going to search through the string looking for the character. But we can. What we want to do is only evaluate that split one time. So there's something called path.hoist. And using that, I can hoist that string.split out entirely. It now becomes a ref variable. And it's a string.split. So it's going to actually be the array for all of these intermediate strings, the split strings. And it's going to say ref.include. So we've gone back to the same JavaScript runtime value, but we've transformed it in a way that allows us to save bytes and save runtime performance. And there's more advanced things we can do, but I don't think I'm going to have time to go through the reverse example where we can put it back. But overall, these kind of AST transformations allow us to target whatever we want. We can make any kind of source code transformation. We can optimize any kind of value. We can save bytes through the AST transformations. Well, thank you, everyone.